write it all out. They don't usually go ask a lot of in-depth stuff for singular value decomposition. They keep it pretty procedural. Just a reminder, so I have this up on the board here. So the singular value decomposition, we're going to write it in three matrices. The sigma is exactly the same size as A. And U and V, U and V or V transpose, they're square matrices. And if A is an M by N matrix, then U will be 4. In our case, we have a 4 by 2. U is going to be 4 by 4, and V will be 2 by 2. That's what it has to be just to get the multiplication to work out. So in our case, with this 4 by 2, we'd have a 4 by 4, a 4 by 2, a 2 by 2. Okay? And U and V are orthonormal. Well, they're orthogonal matrices, which means the columns and rows are orthonormal. Okay, and then next time we'll talk a bit more about the meaning of all these things and how it's used. Okay, questions? Yes? That's okay. Right, oh, so yeah, let's get there when we get there. This one doesn't have 0 as singular values, but we'll talk about when we get there. Okay, so that, for those who are online, the question is, what do you do with 0 as singular values? We're going to have a similar thing creep up in this problem, so we can talk about it. Yeah, it's okay for 0 to have singular values, but it does make it hard to find the columns of U associated with that. Right? Okay, other questions? All right, go ahead and go to work. I do have this up here. I have this slide. A is up there in the upper left. So this gives you the how-to steps, like the step-by-step process on how to do the singular value decomposition. This is right from the video. Okay, take a minute, another minute or two. All right, let's start going through this. This might be a really nice place to start. When you start figuring out the singular value decomposition, is to figure out what size everything should be. This can help you to keep from making mistakes. So start with the center one. It has to be the same size as A. So write down your 4x2 here, and then this has to be a 2x2, so you can actually do that multiplication. This has to be a 4x4, so you can do that multiplication. So you get the 4x4, 4x2, 2x2. So get it all written out like this. So to start off, we're going to look at A transpose A, and we do A transpose A, we get a 2x2, and then we do the eigenvalue. We find our eigenvalues here. So you subtract off the eigenvalue, you subtract off lambda, find your characteristic polynomial, factor it down, you get 16 and 4. Those are not your singular values, right? I have to take the square root of those. So with those singular values, we can already write down sigma. Okay. It's convention that we write down this diagonal thingy. We write down the sigmas, the singular values in descending order. So we start with the largest and go down. The reason is in applications, the columns here and the rows here, the most important columns in U and the most important rows in V transpose, they are the ones associated with the largest singular values. So it gets it so everyone on the same page, and when you're doing the analysis, so you can start to look and use the most important things. So that's just convention. Mathematically, you could swap 2 and 4. You could swap 2 and 4 here. You'd end up swapping the columns here. Like things would swap around. It would still equal A, but it's just convention. Is there a hand up over here? Okay. So why A transpose A and not A transpose? So you can actually do it either way. In our case, it's a lot easier to do A transpose A because you get a 2x2. If you do A transpose, you get a 4x4. But you can find the singular value decomposition of A and the singular value decomposition of A transpose are closely related. And for A, we say, well, you need to find A transpose A. Well, for A transpose, you would find A transpose. I can't do this right. So A transpose becomes your new A. So it's A transpose transpose A transpose. So you get A transpose. So A transpose A gets you on the road to finding the eigenvalue decomposition. I mean, not the eigenvalue, the singular value decomposition of A. A transpose gets you on the road to finding the singular value decomposition of A transpose. But once you have one of these, it's easy to find the other one. This V transpose here is the same. It's this V and the V here are the same. The U and the U here are the same. Sigma here is the same. You just are transposing things and you put them in a different order. So if it's hard, if AA transpose ends up getting you a 2 by 2 or a smaller matrix, go with AA transpose, and then you can just adapt. You can switch things around later. So, like if we were starting, if A have, I'll call it B. If it was 1 0, a negative 3 0, 3 0 minus 1 0, if this is what we were starting with, then do BB transpose to get this, and then we'll fix things at the other end. But, all right. Where are we at? We found our singular values. We found our sigma. Now what do? We need to find the eigenvalues, the eigenvectors associated with our eigenvalues. So we go back to our A transpose A, subtract lambda off the diagonal. In this case, we're subtracting off 16. We get a minus 1, 1. So that means a lot of you would have gone all the way to here because you were really trying to find a basis for the null space of this. This means that x equals y. That's where we got this from. So I know a lot of you can just do this in your head with the 0, 0. So that's just fine with the augmented zeros. Just making sure people understand. Because this is x minus y equals 0. So then that gets you x equals y. A lot of people on the exam, I just finished grading today the 20th problem, the ferret and prairie dog problem. And a lot of people, even if they'd write x minus y here, they would write x equals a negative y. And then they'd lose points. So be careful with that. So you get 1, 1 as a basis vector, but we want to normalize it. So the length is square root of 2, so you divide by the square root of 2. So that's going to be V1. And then you do the same thing here. You subtract off for the eigenvalue 4, subtract off 4, do the same thing, find your eigenvalue, and normalize, and you get V2. And so V1 goes here. So the one associated with the largest eigenvalue we're going to do first because we're putting the largest singular value in the left column. So we get V. Let me write that up over here. Negative on this one. Okay. Oh, but this is V transpose. Okay, so V transpose. So I transposed it really quick to put the negative down. Okay. Now, so we have sigma, we have V transpose. How do we find U? Well, this is number 4. Sam, can you pull up that the slide with the directions? Thanks. So number 4, the first R columns of U we can find by doing this thing. What is R? R is the rank of the original matrix. So we can only get these for non-zero, every non-zero eigenvalue or non-zero singular value we can do this for. We'll fill it out doing another way, but so R is the rank. So I can take the singular value, take A, and multiply the A times the vector the column in V associated with that singular value. So that's what we've done here. So here's sigma. Here's sigma 1, here's A, and here's V1. So we can multiply those, and we end up with U1 there. So over the square root of 2 minus 1 over the square root of 2, 0. Did I get that right? Yeah. And then you do the same thing with U2. Okay? So I think there ought to be like a nice joke or something here. Or I should burst into song or something. A woman needs a man like a fish needs a bicycle. There. Okay. All right. So we take, here's sigma 2, and here's A, and here's V2, and if you didn't get that illusion, you'll have to Google it and find out where it comes from. So, so you do the multiplication, and we end up with another column, U2, another column vector. So okay, and now we've got a problem. This needs to be a 4x4, but we only have 2 columns. We need 2 more columns, and because it needs to be a square matrix so we can do the multiplication, and we want it to be an orthogonal matrix. So we need to have, we need all of these to be to make an orthonormal set. We need all the columns to be an orthonormal set. So what should we do? Yes? Okay, so yeah, a lot of times there isn't just one thing that will work here. We have options. So yeah, so you said take a really good guess. We'll do the easy way first. Okay. So what's the easy? What's one vector that would be orthogonal to these two and would have length 1? There's even an easier one, but that actually also works. So you could. This is what you were doing, right? Yeah. So this works great. And what would your other one be?
The other one I'm thinking of would be negative 1 over radical 2, 1 over radical 2.
Okay, fantastic. Yeah, this is perfectly fine. You're using stuff we know from over here. We know these are orthogonal. We're using the zeros here, but we can write these out. Fantastic. So there are other ones that people had. Let me find this. Kevin? Right, so you're saying just do this. They would. So why not do that? So the reason is these 2 columns, these are an orthonormal basis for the column space of A. And we actually want here, if we continue this process and get something like this, this is an orthonormal basis for the null space of A transpose. And over here, this is an orthonormal basis for the row space of A. And if we had places where we had to fill out over here, then those extra ones would be an orthonormal basis for the null space of A. So So yeah, in some applications, turns out you might not care about these, but it turns out really nice if you do. So you get an orthonormal basis for these are the 4 fundamental bases for a matrix. So you get them all right here. So yeah, right, because anything in this space, like this is a null space, and so anything any part of the matrix you're multiplying by here that has a piece in this space, it's going to go to 0. You're right. So because it's part of the null space of A transpose. But yeah. So we like to fill them out for those reasons. Some applications it won't matter. Okay. Other applications it would. So okay. So there's some students were writing other things. So for example, you could just make this 1 and 0 and this 0 and 1. That's a really slick one. So you'd have 0, 1, 0, 0, 0, 0, 0, 1. Or you could put the 1 here and the 1 there and make the other one 0. Or you could do, yeah, like this. So there's lots of options you could do there. This one's simple enough that you can do it. You don't have to do a lot of work. But if it wasn't that simple, what would we do? Gram-Schmidt. Then you would pick. You'd pick a value, like you'd pick a vector here that's independent of these, and then you would do Gram-Schmidt with that vector, and you'd treat this as v1 and this is v2. And so you'd take the projection of that vector that you picked, the projection of that onto v1 and subtract it, and the projection of that onto v2 and subtract it, and that would give you one of those. And then you pick another vector that would have to be independent of those 3, and do that again. So see why I picked the easy one? So, okay. Questions? All right. Okay, your second task. Boy, where can I put this? Rewrite A as in the outer product form. So use the singular value decomposition that we made here, and let's rewrite A using the outer product form of the singular value decomposition. So work with your neighbor on that. Yeah, so it's there on the bottom of the slide. So. All right, so let's start walking through this. So one of the tricky pieces is making sure you're getting the right column or row over here with V, or V transpose. So I'm going to take this first row, that first column, and I'm going to multiply by this first row of V transpose. Okay? If V isn't transposed yet, then I'd end up taking the first column of V. So, and then transposing it. So that's what the formula shows. So if you've already written it as transpose here, then I can just take that, multiply by this. And like if you do this multiplication, I mean, it will end up being the exact same as this. You can work it out. So, and I'll get that as 4. I get 4 times this column, but I can pull that scalar out and write it out here. And then the next one will be that row, that column times this row, and multiply it by that singular value. So, and then we can go further. We can actually multiply this out. So 1 over the square root of 2 times 1 over the square root of 2 is going to be 1/2. So we get 1/2, 1/2, 0, 0, a negative 1/2, a negative 1/2, 0, 0. But I have to multiply all that by 4, right? Here we're going to have a negative 1/2, 1/2, 0, 0, 1/2, 1/2. Nope. 0, 0. So that ends up being 2, 2, 0, 0, a negative 2, a negative 2, 0, 0, plus 1, minus 1, 1, 0, 0, a minus 1, 1, 0, 0. Okay. So these turn out to be really important in applications because these are approximating matrices to the original. Now, we don't have a really interesting matrix to begin with, but this is the best approximation of a rank 1 matrix that you can get to approximate A. So I think the criteria for best approximation is basically the least squares idea. If you take the difference between each of the entries and square those and added them up, that one will get you smaller than anything else. Okay, like there's a difference of 1 and a difference of 1, differences of zeros, difference of 1, difference of 1, differences of 0. So you basically have 1 squared plus 1 squared plus 1 squared plus 1 squared. You basically have kind of a loss. They call it a loss function of 4. And you can't write another rank 1 matrix that'll be better at approximating it than this. Yes, Braden. A times A transpose. Well, A times A transpose might not even be the same size as your original. Yeah. So those of you in 215, this will you'll do a lab where you're doing picture compressions, right? And this is like your first attempt. And this is what I talked about on the video. I kind of have a simple example where this would be the best rank 1 example, the closest approximation I get to the picture with a rank 1. If I want a rank 2, then I add both of these, and that's the best rank 2 matrix I get. But this is a rank 2 matrix. I get the whole matrix with that, right? So this means I have, I drop 1 in the first column, I add 1 in the second column to those, and I get the original matrix. But this also tells me some structure, and we'll talk about the structure next time. So, any questions? Okay, remember, a woman needs a man like a fish needs a Bicycle. All right. Have a great day.